So this is the video I want to criticise, dealing with relativity from 60 symbols. Why you can't go faster than light with equations. That's the title of this one. Unfortunately, it's in the context of other short videos from 60 symbols, so you can't deal with it in isolation. So let's get started.
We made a few videos about relativity, and we've talked about how distances change in relativity. We've talked about how time changes in relativity. So I thought I'd talk about something which combines those two things together, which is how speed, which is distance divided by time, changes in relativity. The previous videos we made, we called a gamma trilogy because they all had this gamma factor in it. Actually, one of the interesting things about the way speed transforms is that the gammas all disappear, they all cancel out. So there is no gamma in this gamma video. So we need to think about how you measure speed. As I say, it's distance divided by...
Okay, so he's got other videos, and unfortunately have to go to one of them. This video here. Why is time slower in rockets? And he says it's the third in our gamma trilogy. This time Professor Mike Merrifield goes into the mathematics, so the other videos are not dealing with the mathematics, and what I'm doing is I'm criticising the mathematics. So this is the relevant video of the three. It's got the maths in it, so we need to go into the maths now with this video.
This is the third pass we've made of gamma. We had a video on gamma, and then we made another one which we originally called Gamma Reloaded. So if even more unoriginally, we also call this one Gamma Revolutions. Gamma is this factor which comes up all over the place in special relativity. It's to do with, when you have distances being squashed when things are travelling close to the speed of light, the amount they're squashed by this factor of gamma. When time becomes dilated, so time becomes extended, when something's travelling close to the speed of light, the amount is extended by this factor gamma. So it's a very sort of fundamental piece of physics. So mathematically, gamma, this factor, is equal to 1 over square root of 1 minus v squared over c squared. So if you've got an object or a reference frame which is moving at speed v, then its gamma factor is this quantity here. So it's equal to 1 when something's not moving. If v is equal to 0, this quantity comes out as 1, and as v goes up gets closer and closer to the speed of light, gamma gets bigger and bigger. Well, one of the things I said in probably the first and the second video was actually, if you want to derive why gamma has that particular form, it's actually not that difficult to do. And so when you do that, then in the comments underneath the video, quite a lot of people say, well, go on then, do it, go on. So that's what we'll do. We'll do it.
So there you go. In the other videos, he was just talking about relativity, and really he's going to do the math this time. So this is the relevant part. My criticism is of the maths, so here we go.
You're going to do maths? Not very hard. So the hardest maths here is Pythagoras' theorem. Square on the hypotenuse is equal to the sum of the squares on the other two sides. I promise, no harder than that. We need to back up a little bit and talk about special relativity to do this. The fundamental principle in special relativity is that all reference frames are the same, and you can't tell if as long as you're not accelerating, so if you're just moving at uniform speed or stationary, the laws of physics are exactly the same. So if you're in a thing called an inertial reference frame, you can't tell whether that reference frame is moving or whether it's still. You'll end up, if you were inside a closed box in there, whatever experiments you could do, you'll always end up with the same laws of physics. You won't be able to tell I'm moving and that guy is still, or that guy is moving and I'm still. And everyone's sort of familiar with that, right? That basically, if you're on an aeroplane, the laws of physics don't change. If you drop something, if you spill your coffee, it still ends up on your lap. If you put something in the microwave oven still works on the aeroplane. So the laws of physics are the same if you're moving at constant speed or if you're stationary. If you start accelerating, then obviously you can feel the effects of the acceleration. But as long as you're moving at uniform speed, it makes no difference to any laws of physics at all. Next part of the story is electromagnetism.
So, quickly point out a problem here. He's talking about inertial reference frames, and he's not saying what the situation is when it's non-inertial. He's sort of glossing over saying about acceleration when it's non-inertial, and he's not really connecting how that connects to the laws of physics, when it's supposed to be the laws of physics are for inertial frames. So what's supposed to be happening when it's acceleration or non-inertial? He's not really making it clear, and it's the typical sort of fudge these people have when they talk about relativity. They fudge this sort of thing. Their language is vague, and they're not making it clear what's going on. But we're glossing over that. We're just going to get to the maths rather than criticise that too much.
Which says that, so going back to Maxwell at the end of the 19th century, figured out these laws of electromagnetism, and from those he derived the speed of light. The speed of light turns out has a very simple form that is not in some sense a fundamental constant. If you know about electrostatics, how charges attract each other, if you know about magnetism, how magnets attract each other, then actually you can derive what the speed of light is. So the speed of light just comes from simple physics. It's not something that is just a made-up number. It's actually, you can put in some simple physics and derive what the speed of light is. That means that because it comes from simple physics, that means that the speed of light has to be the same whatever reference frame you're in, right? Because it's just come from some simple physics, and the laws of physics are the same.
I would dispute all of that. None of it follows, but he's not actually going into the mathematics of it. So can't start criticising the maths mistakes he's making when making all those sort of claims. So still passing on that and carrying on.
Whatever reference frame you're in, so whatever reference frame you're in, you should always see the speed of light equal to the speed of light. Now to get to how we actually get to gamma. To do that, we have to think about clocks, because clocks are one of the things that get affected by travelling close to the speed of light, that time slows down. And of course, if time's slowing down, that means the speed at which clocks are going is going to change, but everything's going to change. The speed at which radioactive decay occurs, the speed at which you age, everything is going to change. Just because if they didn't all change together, then you'd know there was something funny going on, that suddenly, I'm only living 15 years instead of 75 years, and therefore clearly something's changed with the laws of physics. So any clock you choose to use, all other clocks have to mimic its behaviour. So in special relativity,
I think that's all arguable as well, but it's not presenting the maths for that sort of thing. He's making these claims, not presenting the maths, and so we just have to carry on as he talks away about things before he even gets to the maths.
When you want to derive this equation, you can kind of set up a rather special kind of clock, a thing called a light clock. And so instead of having a pendulum that ticks backwards and forwards, 1 tick per second, what you actually have is, you imagine you have a light source and a mirror. And what you do is you fire out a burst of light that goes up, hits the mirror, bounces back, comes back, and then you've got a little detector next to the mirror which says, whenever I detect some light, I'm going to send out another burst of light. So really you've just got little bursts of light going backwards and forwards. And it's just like a pendulum clock in that sense, that actually is sort of ticking backwards and forwards between there. And so you could use that to measure time. It's not a very sensible way to measure time, but it's a perfectly good way of measuring time. And whatever time you measure with this light clock has to be the same as what you measure with your pendulum clock or your radioactive decay or whatever it is. All right, so now we need to think about what happens to such a clock. So let me draw a picture of it. So here we've got our light source, we've got a mirror up here, and we've got a little detector here. So
all that, of course, is arguable about what he's saying about clocks, but once again, he's not given the maths for that, and so we're just now getting to the maths of handling the light clock. And so this is where we can start arguing about the maths and things.
All times, all you're doing is you're firing some light out there, bounces back, gets detected, and then you've got a little thing that says, okay, whenever I detect some light, I'll send another pulse up, backwards and forwards between these two. We'll make this distance a distance h. And if our clock's ticking, supposing its period is tau, so it takes a time tau to go from there to there, and a time tau from there to go from there to there. So that's analogous to like 1 second on a pendulum clock, because a pendulum actually only completes a period every 2 seconds. So it goes one way for a second and then the other way for a second. So this is going to be a clock that's probably, if we make it, the trouble is if we wanted it to be a second between ticks, this thing would have to be 300,000 kilometres long, which is not terribly practical. So it's probably going to have a shorter tick, but we can write tau if we want that h in terms of the period is c times tau.
So tau is the time interval, and h is the distance, and c is the speed of light. So speed of light times the time interval gives you a distance, and it's supposed to be this distance.
So basically it's tau.
So this rocket, the light pulse is going up and down if you're inside the rocket, but if you're moving along, if you're outside, you're seeing, not seeing that, you're seeing the pulses go in a zigzag sort of pattern.
From our perspective, we're seeing this whole thing moving to the right, so actually what we see the light doing is instead of going straight up, we see the light heading off in this direction, hitting the mirror, as the mirror's moved to the right, by the time it hits it, and then coming back down again, and of course by the time it gets back down to the detector again,
zigzag.
the detector's moved to the right again.
So I'm just accepting that this is what physically happens. If you're seeing this rocket moving along, then what you see for the light is it going in this direction. Whereas if you were moving along with the rocket, you would see the light going up and down. So I'm just accepting that that's what physically happens, as per what he's saying. Some people sort of dispute that, but this is from what physically is claimed to happen. They're then going to start deriving the maths.
So the light, instead of going straight up and down, follows a path like that. So it has further to go. From our perspective, that light's gone further. But also, the speed of light is the same in every reference frame. And so the light's got further to go.
So the claim that the speed of light is the same in every reference frame. I want to highlight that's what he's saying. And it's not really clear what he means by that at this stage. And I'm going to dispute it's still not be clear what that means as you go further on. But that's the claim. Whether you are in the rocket or you are observing the rocket moving, the speed of light is supposed to be the same, whatever that's supposed to mean.
Go, and it's travelling at the same speed, so therefore it takes longer to do it.
So also I should have added that what we're considering is the light being in a vacuum and not being under the influence of any forces. So this is an idealised situation of dealing with inertial frames. Both the rocket and the person observing the rocket are supposed to be in inertial frames. I should continue.
So one of those ticks in our reference frame takes longer than it did in the reference frame in which the clock was stationary, just because the light's got further to go and therefore.
So I'm disputing that about the time. But we'll get onto this, get onto the maths.
And we can fairly straightforwardly mathematically figure out how much longer it's going to take to do it. So let's go back to the picture again for a second. So this is still this distant h. That hasn't changed, which we've already said is equal to c times tau. That hasn't changed. That's our ticks that it would be. The light is now moving at the speed of light c. We see it moving, and it's going to take us some time t to get where it's going. So the distance the light's travelled along here is the speed of light times how long it takes to get there, c times t. Great. And then remember, this thing is moving to the...
So hold on then. So time interval here is what he calls tau. Time interval here is t. So the light goes from here to here in time interval t, and it's supposed to be for the person who's stationary who's stationary with respect to the rocket, i.e. because he's in the rocket, he's going to have this distance, and this time interval is going to be tau. So they're saying they're different time intervals.
Right, it's moving to the right at some speed v, which means by the time the light has got to the top here, this thing will have moved the distance over here. How far will it move? Well, if it's moving at speed v and it's got a time t to do it, then the distance it travels is just v times t. And this?
So, hold on then. The time interval here is t, time interval here is t, and the time interval here is supposed to be tau. So, what's going on here? Surely it should be some speed here times t, the time interval t, not tau. So it should be, you should expect that for a start this speed times a time interval would be t, not tau. And then you'd wonder, is the speed actually c or some other value? So something funny is going on here. T here, and tau here. What's going on here? Different time intervals. It's supposed to be the time interval along here is t, time interval along here is t. You would expect the time interval would be along here to be t as well, just from that. But no, you're going to make that a different time interval, which is a bit confusing.
This is just a right angle triangle we've got here. And so we can apply Pythagoras' theorem, which says that the hypotenuse squared is equal to the sum of the square.
Yes, so it's Pythagoras theorem. You've got right angle triangle, Pythagoras theorem. Just going to accept that that's the sort of maths he's going to use for now.
On the other two sides. So ct squared is equal to c.
So that's the hypotenuse, and those are the two other sides, c tau and v t. So the square of the hypotenuse equals the sum of the square on the other two sides. So that's Pythagoras theorem. And sort of the query bit is, you've got t there and t there, but you've got a different time interval here, tau. So it's different. What's going on here? Let's carry on.
Tau squared plus bt squared. So let's just write that down. We've got c squared t squared because we squared the whole thing. So it's c squared tau squared plus v squared t squared. Now I need to do a little bit of...
So that is the same equation from earlier, and now he's going to manipulate it. He also has the diagram here from earlier, same as earlier.
Magic to rearrange this formula. T squared is equal to tau squared over 1 minus v squared over c squared. And then I just take the square root of both sides. That tells me that the time I measure in my reference frame is the time you measure in the reference frame in which the clock is stationary, divided by, and I've got to take the square root of the bit on the bottom, 1 minus v squared over c squared, which is just gamma, as we defined before, times tau. So the factor of...
So that is the equation he has derived. Time interval t equals gamma times tau. Two different time intervals, and they're connected by the gamma factor. There you go. And that's what he's given us. So we go back to earlier. I'll go back to the earlier diagram, which I probably can't find now. He's got this diagram. Put it up on here. Just the way I've drawn it. You've got CT on that side, VT there, and C tau there. Okay. And he's given us the connection between T and tau as this equation. So tau equals T divided by gamma. If we substitute that now into the triangle, for that side c tau, that means it is c times t divided by gamma. And you say, hold on a minute, why are we having that? Why shouldn't it be c divided by gamma, and that's times t? Bracket that. So the speed along here is really c divided by gamma, and then the time will be t. Time interval is t. Time interval t there, time interval t there, and then it will be time interval t along there as well. So it's a case of that, instead of c times tau, which is that. So the speed along here is not c, it is c divided by gamma. So this mess with the time intervals is just because he's trying to say that the speed along there is c, when it should be c divided by gamma. So he's making a mess of the maths just on that. Or he has to explain why he is going with that equation instead of that. Why is he putting t divided by gamma when he should be going c divided by gamma? He hasn't gone into an explanation of that. He has just glossed that over, and that is one of the little fudges they do. They just gloss over explaining themselves properly. So, not explaining himself properly there. What's he doing? It is a typical thing that they do, that they don't go into sufficient explanation of what they're doing. So we have t is equal to gamma times tau. Another little trick they do, so if we go, that is the equation he's given us. Another little trick they do is they sometimes write that differently. They sometimes write it like that, where you've got this, which is a Greek letter delta and a Greek letter delta here, and that's trying to emphasize that that is a time interval. That's a small interval of time. So that's basically a time interval t is equal to gamma times this time interval, and instead of having it as tau, they have it as t with a dash at the top, which is prime. They call that t prime. So they sometimes write it differently, and that's another little fudge they do. They try to confuse you by using different notation all the time. So I want to emphasize that when he's giving you this, he's really giving you that as well. That is just it written a different way. And so when we go back to the other video, we should remember that. Here we go. So back to his other video, why you can't go faster than light with equations. He's going to use, well no, he's not going to use, he's already established that equation, and in different notation it's written as that. So we can carry on now with him talking about relativity.
But particularly how it changes depending on what reference frame you're in. So we need to think about how different people measure speed in different reference frames. And so the classic kind of thought experiment you might do is you've got somebody on a train, and we'll call what you call this reference frame S prime, and they're going to roll a bowling ball along the train at some speed or other. and the train itself is moving, so this whole reference frame.
So this is sort of like the reference frame S prime, that dash up there is making it prime, S prime, and it's referring to this person who's having this speed for the ball as U prime.
Is moving, if you like, in this direction at some other speed V. And so the way on the train you'd measure the speed is that you'd see how far the bowling ball had gone in your reference frame, which we call this delta x, how far it's gone, prime because it's in your reference frame, and at what time, you know, you'd measure that at some time delta t prime after you let go of the ball, and then you could actually measure the speed in your reference frame of that bowling ball. It's just how far it's gone divided by the time it took to get there. Like that's the definition of speed, is how far.
And this is in the S prime frame. You have a U prime is equal to this distance divided by the time interval. We're using delta as trying to emphasise it is an interval of distance, interval of time.
Something's gone divided by the amount of time it took to get there is the definition of speed. So that's in one reference frame. So then the question is, what does the person in this reference frame, the other reference frame, see? And
so this is the other reference frame. This person is reference frame S, and you should really emphasise these are inertial frames again. I think it needs to be referring to inertial frames because he's not. I don't think he's stated that, but I think that's what it's supposed to be. So this person in the S inertial frame and this person in the S prime inertial frame. So this person is getting this, and so what's this person having?
And let's deal with the non-relativistic case first. Okay, so what are they going to measure? The distance that they'll measure that ball has gone is going to be how far the bowling ball's rolled away from you, plus how far you've moved down the line. That extra distance, how far the train has moved, depends on, well, that's basically how fast the train was going.
You're sort of adding it all on top of each
Yeah,
other.
exactly, that's all you're doing. So that distance is V delta t. The train's going at some speed V, and it's travelled for some time delta t, then the distance it's covered is just the speed times the time it's taken to do it. So now we can put all this stuff together that says that delta x is equal to, so how far you see the ball as having moved is how far the train's moved, plus how far the ball was moved relative to the train, just the sum of the two. And we can rearrange this in non-relativistic case to say that let's just divide through delta x divided by delta t is equal to v plus delta x prime divided by delta t. And in this non-relativistic case, we don't have to worry about different people seeing different times, so it doesn't matter whether that's delta t or delta t prime, we can call it the same thing. So
I'm going to let that pass. He's saying that in the case he's talking about that t is the same as t prime. I'm not going to get into that. I'm going to let that pass. Okay, let that go for the moment.
the same thing. Or we can rewrite this again. It just says that the speed that you see the balls moving is equal to v, so that's delta x by delta t, plus the speed that the person on the train sees the ball moving. And that, as you said, is just basically you just add the speeds, right? The speed at which the bowling ball is moving is the speed that the ball is moving relative to the train, plus the speed that the train is moving relative to you. Right? That's the simple Galilean transformation, no relativity. Everything works sensibly in the way we're used to it working.
Used to the way it's working, they did talk about is Galilean and so forth, but really it's just Newtonian physics. So Newtonian physics, it would just add like that. Newtonian physics, that's just Newtonian physics, that's the way the speeds, if you're considering it in that direction, would add. Gets more complicated if you're talking about velocities going in different directions. So if that's a velocity going in different direction, that gets more complicated. But as long as they're going in the same direction, then you can add them quite simply. like that, speed in that direction of that, and the speed in that direction of that. You just add them together to make the total easy enough, and that's Newtonian physics. Try to pick him up from where he left off. Here we go.
The reason why people get interested in this is that one of the things that everyone says in relativity is you can't ever travel faster than light. Right? And so one obvious question you could ask is, well, why can't I just get to travel faster than light by doing these kind of additions? Supposing instead of rolling a bowling ball, the person on the train was actually shining a torch along the train, then the torch beam would be travelling at the speed of light relative to them. And then if you ask, well, how fast would the torch beam then be travelling relative to you? Well, it would be the speed of light plus the speed that the train's moving away from you, and that's faster than the speed of light.
No, you've hacked
Exactly.
the universe.
It's sorted. Unfortunately, relativity takes care of that, and it's not really the way that things work.
So I dispute all that. He's trying, what he's going to state, what all those claims he's making, he's now going to show the maths for it, and I'm saying, well, the maths he's showing doesn't really show what he's claiming here. So we get to the maths now.
We need to start again, but we need to now do the problem properly with relativity.
Is this your minute physics audition, Professor?
Unfortunately, my drawing is not quite up to the job, I suspect. And then we got the other chaps in here, moving along at some speed v. Okay, now previously the formula we had said that the distance,
So once again we've got the S frame and we've got the S prime frame. So he's doing the same again, but now it's supposed to be by relativity.
the bowling ball is down the line is equal to the distance on relative to the train plus how far the train's moved. Now, the extra factor that we haven't put in yet is special relativity, and as we saw before, what special relativity does is introduces these factors of gamma. And so this Galilean transformation that we had before is a little bit modified by an extra factor of gamma in front of it. Gamma is 1 over the square root of 1 minus v squared over c squared.
And he hasn't shown why you're multiplying this by gamma. He hasn't shown that. He hasn't shown that in the previous videos. All he's done is shown gamma in that equation. He's not shown gamma being used in this way. He's not shown why you're going to multiply that by gamma. So it's another flaw in his presentation. He's sort of telling you something and he's not showing you why. Why is that? And if you did show why that, I would dispute that as well, because I've seen people who have tried to present a case for multiplying it by gamma, and I would dispute that as well. But he's not actually given a reason for why you should multiply by gamma. He's just saying do it, just multiply it by gamma. So it's out, plucked it from nowhere. He's plucked it out of a hat, like a magician plucking a rabbit from a hat. And this is a typical trick people doing relativity will do. They'll just pluck equations out with no reason behind where they're coming from. They suddenly, oh, we're going to put a gamma here. What? Why? No reason, just feel like it, and then we're going to call it relativity. What? Huh?
We have a whole series of videos you can go and watch about gamma should you wish to do so.
Yeah.
But then the other thing we know
And
about relativity is
those
that
videos, as I pointed out, don't deal with that. They don't tell you why you're going to put that gamma there. So he's kind of bluffing you.
only does the distance depend on what reference frame you're in, but actually the time depends on what reference frame you're in. And so we need the equivalent transformation for that. So there are these things called Lorentz Transformations. That's the first of them, and then this is the other Lorentz transformation we need. Turns out these are the two Lorentz transformations you need. Okay.
So he jumped, got over there. So didn't stop in time. Go
There are
back.
these things called Lorentz Transformations. That's the first of them, and then this is the other Lorentz.
So here we go. he's plucked another equation out of nowhere. Suddenly, well, here you go, here's another equation. Where's it come from? What's the reason for that? And from the video which dealt with the time dilation, what he had gave you this equation. That's the maths he's shown. He's shown you that, and I've disputed that. I disputed why is that, but now we're sort of like, okay, we accept that equation and go on with it and say that's what you've got last time. Okay, we accept that, even though we dispute why you got that. And in the different notation he's writing it as that. It'll be written as that. And so he's got down this. He's suddenly got an extra term. He's sort of like, previously you just had that. You just had that bit of it. And suddenly you've got an extra term now. Where's this coming from? Suddenly, something else plucked out from thin air. You said, what? More conjuring tricks. It's not. This is not proper mathematics. It's not showing you the steps of what's going on. It's sort of like magic. It's just out from nothing. It's nothing substantial to as a mathematics. And this is a typical thing that they do. They just typically throw maths at you, and it's not shown properly where's it coming from. Of course, if this person was showing you where these equations were coming from, I would still dispute that. But he's not showing you where they're coming from. So suddenly you've got these equations which have come from nowhere in the way he's presented it. So I'm particularly criticising his presentation. If he put his presentation together better, I would still find fault with it. If he went by what the textbooks say, I would still find fault with that. But he's not doing that. He's not going by what the textbooks say. I would criticise that as well. But he's worse than the textbooks. He's just plucking out equations from nowhere.
Transformation we need. Turns out these are the two Lorentz transformations you need. Okay, so now we can say, okay, so what's the speed as measured from the person who's standing beside?
So we've got these equations. We don't know where they came from. We just have to see what's he going to do with them. Even though it doesn't make sense where they came from. It doesn't make sense in the context of what he said about time dilation earlier. But carrying on, just have to accept the math for now and see what he does next.
Beside the track, watching the train go by, and we just do the same thing that we did before. The speed is just the distance divided by the time. So we can just divide them. Delta x divided by delta t is equal to. Now the gammas are going to cancel because we divide that by the other. We end up with a gamma on the top and a gamma on the bottom, so we can just cancel them out. And I'll do a little bit of tidying up. I'll divide top and bottom through by delta t prime, so I can just write this as delta x prime over delta t prime. This is kind of the answer that we wanted, because delta x over delta t is the speed of the bowling ball or whatever it is that's being thrown along the train as seen from the person standing beside the track. And delta x prime over delta t prime is the speed as seen by the person on the train. So I can write that in terms of the u's and u primes before. This just says that u is equal to u prime plus v divided by 1 plus, that's a u prime again, v over c squared, which is the final answer. In the non-relativistic limit, so what we were looking at before, the Galilean transformation, so both u prime and v are small compared to the speed of light. That means this term is small, so this thing's just 1 basically, and that just says that the speed you see is just the sum of the speed of the ball relative to the train and the train relative to you.
Right, so now this is going to get pretty complicated in the way that he's messing things up. So even though we dispute how he derived this equation, just going to have to accept it. So there you go, that's the equation he's got there. previously, when it was Newtonian physics, it was this equation, but now when it's relativity, it's supposed to be this equation. And so, do we notice anything? Well, that u is not the same as that u there. What? If that u is the same as that u, then you wouldn't have that there. It'd be that's just over 1, not over that bit. So that u is different to that u. So it's not the same thing. And so I would write it in a more complicated way. I would write the first equation as that, and the second equation as that. I would put a subscript r there, a subscript r there, a subscript r there, and there, and there. And that r is to represent relativity. And the n there would be to represent Newton. Newton there, there, and there. So that is a Newtonian speed, and that is a relativity speed, and they're not the same thing. Similarly, that is Newtonian speed, and it's not the same thing, is that? That's the relativity speed. So this is just bad notation. By saying u equals that and u equals that, they're not equal. They're not the same thing. Unless that is 0. If that is 0, then that u does equal that u. But if that's not 0, then that is different to that. And this is the bad way that people handle the maths for relativity. They just don't care. They're just going to tell you that's u and that's u. And it's sort of like, no, they're not the same thing. It's the math. They've messed the maths up by not emphasising that is different to that. So we've got to bear that in mind, that that's what he's doing. And it's supposed to be that when these are speeds that are very much less than the speed of light, then this equation approximately equals this equation. So they're not supposed to be exactly the same. They're supposed to that equation is supposed to approximate to that one for speeds that are much lower than the speed of light. But anyway, let's carry on. So when he means a more interesting case, he means when it's considering, like when it's one of the speeds going to be light speed c.
So in that case, we end up with, if u prime is equal to the speed of light, then u is equal to, u prime is just the speed of light plus v divided by 1 plus u prime is the speed of light, cv over c squared. Now we just do a little bit of playing around with this. So I'll rewrite the top here as c into 1, so I'll pull that factor out, plus v over c.
When they do, this is sort of like a maths trick really, is rearranging the equation to get it all reduced down to c.
So if I multiply this out, I just know there's c plus cv over c, which is just v, so c plus v, divided by, and then all I'm going to do here is cancel the c over c squared, so I end up with 1 plus v over c, which you'll notice is just the same as the term there. So this is the same as that, which just basically means that this whole thing is just equal to the speed of light still.
Okay, so rearrange, and then that turns out to be c.
So there's the bizarre thing that we've taken. What we've done here is said, okay, so there's a light beam that's moving relative to the train at the speed of light. Now, if you're watching from beside the train, what speed do you see that light beam?
Yeah, so this is so that's supposed to be light speed c relative to that, and he's not making it clear. This person, what's he saying? Is he saying that is light speed c relative to there as well, or is he just trying to having something else like light speed relative to him as c? And so the ambiguities like that they rely on, and he didn't when he talked just then, he didn't make it clear.
Going at, the answer is still the speed of light. You haven't actually added to its speed.
So you got the u dash, or the u prime is equal to c, and u equals to c. Or is it just that speed relative to this? So it's the person saying here, I'm stationary. He's in a stationary frame, and he's saying, oh, light speed relative to me is c. And this person here could be saying, oh, I see you're moving, but relative to you, what you've got is a light speed c as well, which is not quite the same thing as what is the light speed relative to this person.
And I guess the physics behind it is that actually you really have to worry about both space and time being changed by what reference frame you're in, which means that, not surprisingly, the speed that comes out at the end is going to be changed.
So he's not, so having been ambiguous earlier, he is now not making sense.
Slightly strange way as well, and it turns out that relativity takes care of this invariance of the speed of light. That no matter what reference frame you're watching the light beam travel from, you'll always see it travelling.
Because he's not gone into sufficient explanation about the maths. So if we can go back again.
Still the speed of light. You haven't actually added to its speed at all. And I guess to cancel the c over c squared, so I end up with
Here we go.
plus v over c, which you'll notice is just the same as the term there. So this is the same as that, which just basically means that this whole thing is just equal to the speed of light.
So back to this equation. Yeah. If that is 0, then that equals that. Okay. So he's found out whether this equation, if you go in c plus v is equal to c, well, from that equation, if it's u to subscript n, and that's dash, plus v to subscript n, if you add those together, say that is c and that is c, well that would be 0. So is this v supposed to be 0 or not? So you go in c plus 0, 1 plus 0, that all comes out as 0, and that comes out as c. So that equation is valid for v equals 0. But he's trying to tell you that in relativity that equation is also valid for v other than 0. If say v was half the speed of light, he's trying to tell you that that equation would still be valid. So if you add c plus half the speed of light, he wants to say that it comes out as c. But he hasn't shown that. He hasn't shown that it's valid. He hasn't shown what values of v is this valid for. So it's all just bluff. It could be that the only value of which this is valid is for v equals 0. You're adding c plus v and getting the c as the answer, then it may be that it's only valid for v equals 0. And he hasn't shown otherwise. He's not gone sufficiently into the math to show what's going on. So we go on to the next little bit. Oh, sorry, pick it up from here.
What we've done here is said, okay, so there's a light beam
repeating what he's saying.
The train at the speed of light. Now, if you're watching from beside the train, what speed do you see that light beam going at? The answer is still the speed of light. You haven't actually added to it.
So, what has he done? This one's saying u prime is equal to c. This one's saying that u equals c. So, he's saying the speed of the light relative to him is c. This person here, what's he saying? Is he saying the speed of the light is c relative to this person? Well, that would make sense. or is he saying the speed of light is c relative to himself? The equation which he's given might just be telling you that the speed of light relative to him is c, and this person in this frame says that, and this person in this frame is also saying that it's relative to him as c. So he's not said anything. He's not gone into explanations here about what is supposed to be going on. He's not shown it. So he carries on talking.
And I guess the physics behind it is that actually you really have to worry about both space and time being changed by what reference frame you're in, which means that, not surprisingly, the speed that comes out at the end is going to be changed in a slightly strange way as well, and it turns out that relativity takes care of this invariance of the speed of light. But,
so he just carries on talking out garbage, basically. He's not shown properly how the math is handled in relativity. He's not shown anything. He's just glossed over everything. And this is a typical way they do it. They sort of like build up. We go back to the earlier. We start to build up. I complained about what he was doing with that. It didn't make sense. He didn't go enough explanation. What's he doing with this equation? And then later he's going to use a different notation where you can actually use a different notation for it. But then he uses a different equation than this one. He doesn't explain why. And then he goes into, well, instead of explicitly making that these two equations are different by putting, say, a subscript n on it and a subscript r here, by not explicitly making the difference, he's glossed over it again there. And so the whole process involved is making a mess of the maths. He's not explaining properly what is going on with the maths, and he just keeps building upon it. And so at the end he's talking about the physics of it, which is just all based on maths being messed up. The physics is not there anymore. The maths is just messed up. Whatever he's saying about physics, the time transformations and all that sort of stuff, it's just all garbage, and it's just being built one thing on top of the other all the time. By one step, the initial step not making any sense, and then carry on, ignore the fact that it doesn't make any sense and he's not gone into sufficient explanation to clarify what's going on. He goes on to the next step, and that step doesn't make any sense as well, and then he goes on to the next thing, and the next thing, and the next thing, and the next thing. It's just all built on top of each other. It's just a total mess in the mathematics. And then, having made a total mess of the mathematics, he's then going to say a load of stuff about the physics. What does it mean for physics? So what's he saying? What's he saying? He's got here, go back to the physics, he's got this person here and this person here, and what are they saying? They're saying the speed of light is the same. But what are they talking about? What speed of light are they talking about? Are they just talking about the speed of light for this person is c, and this person is agreeing that the speed of light for this person is c, but they're not saying anything. They're not saying anything interesting. They're saying, well, that person's saying the speed of light is c for this direction, and this person here saying, yeah, I agree with you. What you're getting is the speed of light c. And the person's saying, well, you got the speed of light c here, but I can see that you're moving with a certain velocity, and so relative to me, that speed which you're saying is c is not c. It's a different thing. He's taking account of speed here, but no. What they've done is they have this mess with the relativistic velocity addition. This is what they call relativistic velocity addition. All this. So it's not making clear what are they doing with that. So when they're making these claims, why you can't go faster than light with equations, Well, it's just a total mess in the maths. Total mess. Not gone into sufficient explanation as to what is meant in each step of the maths. This all just doesn't follow. Why you can't go faster speed? What from that? Hasn't explained himself at all. And what does he get? He gets 6.8k likes. This is 6,800 people approximately say that's good. So 6,800 people watch these videos and say, yeah, that makes sense. That makes sense to me. And it's sort of like, it shouldn't make sense to you. He hasn't explained what's going on. You think it makes sense. You have deluded yourself. This person who's talking to you hasn't explained things properly. Let's pull him up again. He thinks he knows what he's talking about, but he hasn't gone into sufficient explanation what he's doing. It's just a big fudge in the maths. So he's ended up with a mess. It's meaningless, gibberish. Thank you.